Alright, so we're back to Scala at Lightspeed. So I just mentioned in the previous video that the Scala at Lightspeed mini course is closing, and here I am with another lesson. This is Daniel for Rock the JVM, and in this video I'll show you contextual abstractions specifically in Scala 3. The rest of the mini course works just fine on both Scala 2 and Scala 3, and in this video we're going to write specific Scala 3. So let's move back to our project, and under com.rockthejvm I'm going to create another Scala application. I'm going to name this Contextual Abstractions, and I'm going to make it an object as before, just in case we need to test something, and I'm going to add a main method. Now make sure that your project is specifically set up with Scala 3, which you can find here under build.sbt, or you can go to I think it's File and then Project Structure, and here you'll find the Scala version that you created your project with. So let me collapse my file explorer and let me show you what I mean by contextual abstractions. This lesson will have two big techniques that will give Scala some extra power and extra expressiveness. The first set of features is called context parameters, or arguments. And I'm going to show you shortly what I mean by that, and this will also motivate the name of contextual abstractions, which is quite vague, but frankly I couldn't find a better name myself. So I'm going to start with a simple example. I'm going to define a small list, let's call this a list, and I'm going to create a list of numbers, and I'm going to specifically enter them in a different order than the ascending ones. So I'm going to say 2, 1, 3, 4 or something like that. Now, the list data structure, much like most sequences in the Scala standard library, has a method called sorted. So I'm going to say, let's call this an ordered list. I'm going to say a list.sorted. Now, sorted doesn't take any arguments, but if I print line the ordered list, and if you run this application, it'll take a couple of seconds for this thing to compile, we'll get the list 1, 2, 3, 4. And the list is magically sorted in ascending order, as if the compiler knew by magic what the natural ordering of ints should be. Now, from your existing programming experience, you may have done a bit of sorting of collections yourself, and you probably are aware that whenever you want to sort a collection, maybe a list or an array or what have you, you need to pass some sort of comparison function. So something like a comparator object, or have the elements be comparable themselves, or some other form of telling the runtime which element is quote-unquote less than another element, so that we know which element needs to stay first and which element needs to stay last in the sorted collection. Now, in Scala, we have an existing comparison function or comparison object, and that is called ordering. Now, an ordering is pretty much a glorified two-argument function that says which element is less than another element. So I can define, for example, descending ordering as ordering of int, and the type ordering comes predefined in the Scala standard library. And I can build an ordering object by saying ordering from less than. So you're basically wrapping a two-argument function that returns a boolean, and the boolean says the first element is smaller than the second element, with smaller than in air quotes. So I'm going to say, for example, underscore greater than underscore. So this is the shorthand lambda notation in Scala that you may have seen in the previous video. So that's essentially a b arrow a bigger than b. So I'm basically saying that given two elements a and b, a is quote-unquote less than b, so a should stay before b if a is greater than b in the mathematical sense. Alright, so this is what the ordering object will do. And here in this lambda, you can define your own logic for comparing numbers. Now the thing is that the compiler can automatically sort a list by having access to some value of ordering int that comes pre-built with the Scala standard library. So this instance of ordering int, which denotes the natural ordering of integers, is automatically fetched by the compiler somehow and injected into the argument of the sorted method. So we say sorted, but in reality, it actually has an additional argument that has an ordering which is automatically injected by the compiler. Now, in order to be able to inject our own ordering into the sorted method of a list, we are going to make this descending ordering thing, or whatever ordering we might want to use for the sorted method, and we're going to make it a given. Now, a given instance will be automatically fetched by the compiler for every single method that takes a so-called magical phantom argument here of type ordering int. So in this case, for a list.sorted, the compiler will not fetch the given ordering of int, which is the natural ordering of integers built in from the Scala standard library, but it will rather use this given instance that I've defined. So this will actually be injected with the descending ordering that I've defined here in this scope. So if I run this application again, we're going to see the list sorted backwards this time around. So we see list 4321. So this is quite magical. Depending on the kind of given instances that we define in the scope where a method with these kinds of arguments is being called, we can change the behavior of that method. Now, the phantom argument to the sorted method is actually called a contextual argument. So sorted actually takes an argument list, but that argument list contains an element or an instance of type ordering int, which is contextual. So depending on the context where the sorted method is being called, the compiler will fetch whatever given instance it has access to within that scope. And with that ordering int, the behavior of sorted will give you back different results. So if I had not created this given instance, then if I run this application again, the compiler will fetch whatever given instance it may have access to from the Scala standard library. So we get list 1, 2, 3, 4 from the natural ordering of integers. If I create my instance of descending ordering with my own logic, then the behavior of sorted changes and we get the list sorted backwards. Now, if you want to make an analogy to the previous video where we talked about implicits, a given instance is analogous to an implicit val. And because the Scala 3 standard library is still very young and implicits are going to be deprecated in future versions of Scala 3, so the sorted method takes an implicit value of ordering b. So this will be the phantom argument, the contextual argument that I mentioned here that you can solve or that you can pass automatically through the compiler by creating a given instance of ordering in the scope where the sorted method is being called. Now, in Scala 3, you have the ultimate freedom to choose whether your methods that you want to implement in your business logic will support this sort of behavior that will take contextual arguments and having different behaviors depending on the scope or the context where they're called. Let me give an example. So I'm going to define a trait. I'm going to call this combinator, and I'm going to type it with the type argument a, and this combinator has a simple method called combine, and it will combine two elements of type a, so x of type a and y of type a, and it will return another element of type a. Now, an example of combinator would be something that sums two integers together and returns their mathematical sum. Now, technically, mathematically, this is called a monoid, but I'm going to revert to the combinator name because it's much more descriptive. Now, assume that I'm going to define a method called combine all that takes a type argument a and a list, which is a list of a, and this returns an a, which is the result of collapsing all the elements of the list into the same value given by the logic of a particular combinator. So I'm going to pass a combinator here as a second argument. So I'm going to say combinator as a combinator a. Now, when you write something like this, in practice, there are several wishes involved in such methods. First of all, your API, this combine all, might get quite big and quite cumbersome and boilerplatey at the call site. So whenever you want to actually use combine all on a bunch of lists, you always have to pass the right combinators of those particular types. And especially if you use this often, this might get quite annoying. The second wish is that you might simply want to not care what the local combinator rules are at the call site of combine all. So you might want to ideally call combine all on the list 1, 2, 3, 4, and not really care what the combination logic will be for the call side here. Maybe you're doing some math library and combine all for list 1, 2, 3, 4 naturally sums them together. You don't really need to pass a combinator which sums up all the integers every single time. Now this may sound like a first world problem, but in reality this kind of call or this kind of code would actually quite dramatically improve the quality of your code and the quality of your development life. So in order to be able to grant this kind of wishes, then we would add a context argument here to this combine all method. So we would make the combinator A be a contextual argument by using a keyword called using. So when you say using combinator as combinator A, the compiler will need to take care to pass the appropriate combinator A whenever you call combine all if you have a given of that type in scope. And I'm going to show you how you can use that shortly. Let's implement this real quick. So I'm going to say list.reduce, and I'm going to pass a 2-argument function that is based on the combiner. So I'm going to say combinator.combine. Or if you prefer the longhand notation, I can say AB, arrow, combinator combine with A and B. All right, so I can say list reduce on this lambda, and this lambda will take care to collapse this entire list under the combination function of the combinator. Now, this structure with the context argument does two things. Let's say that I define the sum of all the numbers in a list, and I'm going to call combine all, so combine all of that particular list that I defined at the beginning, so I'm going to say combine all under a list. Now, the contextual argument here does two things. First of all, if we don't pass a combinator here and the compiler cannot really find anything, then this code will not compile at all because the compiler cannot really inject the combinator logic for combine all. So if I try to run this application or even compile it, we will see a compiler error saying no implicit argument of type combinator int was found for parameter whatever. All right, so we don't have a given instance for the compiler to inject automatically here. Thankfully, if I define a given instance, let's call this int combinator, as a combinator int, and I'm going to define a new combinator real quick. So I'm going to say a new combinator int, and I'm going to say override combine, and I'm going to return x plus y. Then the compiler will automatically pass this one here. So int combinator will actually be passed by the compiler automatically. In fact, you can also check IntelliJ because it shows you implicit hints, that is all the given instances that are automatically passed by the compiler. So you can go here to help and search for implicit hints. And here you have a menu here under view. And if you click that one, it'll show you what values the compiler automatically passes for you. So right now, if I hit on recompile, so I'm going to hit Command-Shift-9 here to recompile my code. Notice that the code can now compile, and I can also print, for example, the sum. And the sum, because I have elements 1, 2, 3, 4 in whatever order, the sum should be 10 because this combinator will sum them all together. So we're seeing the number 10 here in the console. So a contextual argument can be specified using the using keyword here in a separate argument list, and you can automatically pass or make the compiler pass a particular instance of, in this case, combinator int with a given instance in the scope of the call site. And as you saw earlier, if the compiler cannot really find a given instance to inject here in the using clause, then the code will not compile. And I'm going to show you where the compiler actually looks for given instances. So first of all, the compiler looks in the local scope. So in the scope where the actual method taking a contextual argument is being called, the compiler will search for a particular given value of that type in the scope where that method is called. This is called local scope. The compiler then looks for the imported scope, because you can import given instances by using import, and then you can write your package, and then you can say given after that. So when you say import your package.given, you import all the given instances from that package. So the compiler will look in the imported scope for the given instances of that type. And the third place that the compiler will look is the companions, that is the companion objects, the companion singleton instances, of all the types involved in the method call. And in our particular case, the compiler will look for a default combinator int, because we're using a list of integers here in this method call. So it will look in the companion of list and the companion of int, which just so happens that it is the case here for a list.sorted. So in the exception of me creating a given ordering int here in the scope where the sorted method is being called, the compiler will look in this third place, in the companion of list, which doesn't really have an ordering int, but rather it looks in the companion of the int type itself, which happens to have an ordering of int. So the compiler will simply fetch that ordering of int and it will inject it here in the sorted method. So quite a lot of power and quite a lot of behavior change depending on the context of the call site. That's why they're called contextual abstractions. And this is called an abstraction because you're abstracting away, you're basically not thinking of the combinator logic at the call site. You're simply calling combine all a list, and the compiler is only taking care of the rest. So you don't have to care about it, you don't have to think about it. Okay. Right, let's talk about context bounds. Now, there is a shorthand way of using a contextual argument if you're not actually using the combinator instance. So for example, I can define another method, let's call this combine all. I'm going to use v2 here with type argument a and a list as a list of a. And if you're not actually using the combinator instance directly, but you're rather calling other methods that are using a combinator a, then you can simply say using combinator a, not necessarily naming that particular instance. And this will return an a, and the implementation can be whatever. And in that case, there's also an even more shorthand notation for specifying a using clause, because you're only mentioning that you need a combinator a so that the compiler can use it, but you don't necessarily have to name it. So this is only a type restriction for the compiler. So you can say combinator or combine all. I'm going to use v3 here with the type argument a and list as a list of a. And this returns an a. The implementation can be whatever. And in order to mark to the compiler that you need a combinator a in scope where this combine all v3 method is going to be called, you only need the type restriction to a so that the compiler can find a combinator a in scope. So the marker is a combinator. Now, when you read real-life Scala code in your project or at your job and you see a method that takes a type argument and then say colon some type, then that should be read as a marker a must have a given instance of combiner or combinator a in scope. All right, so a combinator is identical to this other method definition that I wrote above. So I think you got the idea. A combinator is a form of type restriction. Let me tell you where context arguments are useful. So they're useful for a variety of patterns in functional programming and in the Scala language in general. Type classes are a massive use case for contextual arguments, and type classes are an advanced feature of functional programming in general, and they're quite outside the scope of this video. I have a bunch more on my YouTube channel. Then we have dependency injection. We have contextual abstractions for using code for some types, but not for others. So context-dependent functionality. That is the capability of restricting a piece of your logic to some types, but not for others, depending on the contextual presence of given instances. And also a quite magical aspect of the Scala language, which is type-level programming. Then type-level programming is a capability exhibited by the Scala language in which the compiler can generate types and prove relationships between types at compile time. This is very, very powerful and also quite abstract, and contextual arguments provide the vehicle for achieving that. All right, so we've talked a lot about contextual arguments. Let's talk about the second part of this video on contextual abstractions, and that is extension methods. Now, the truth is that in the Scala language, you can add additional methods to a type after it was defined, even if you have no control over the source of that type. And extension methods are heavily used in functional programming libraries such as cats or cats effect. And let me give an example. Let me define a case class. So case class person with a name. And this class has a simple method. Let's call this greet. So greet will return a string and say, hi, my name is name. I love Scala. Of course, I love Scala is optional. I hope you do. And after that, I'm going to create a particular structure that you have not seen in this course yet. And I'm going to write the following. I'm going to say extension, which is a contextual keyword in the Scala grammar. And I'm going to say extension string as a string. And I'm going to define a method called greet, which returns a string. And the implementation of this method is going to be new person with that string dot greet. Now, this particular structure will then allow me to write, for example, Daniel's greeting as the string Daniel dot greet. Just like that. As if greet was part of the string Daniel. Obviously, if I had not written this piece with extension string, then if I try compiling my code, then the greet method will not be found because greet does not belong to the string class. But if I write this structure here with an extension, then I will compile my code and it will compile just fine. And the reason is that the compiler normally would not compile the greet call on the string Daniel, but it would search for all possible extension methods on the string type. And because I created an extension to the string type, it will have access to this greet method, which I added later to the string class. And this gives enormous power, and that is because we can enhance existing classes to suit our needs. And this is called type enrichment. And colloquially in Scala 2, that was called pimping a type. Now, the term pimping went out of fashion, and this more boring type enrichment term was a little bit more prevalent in the Scala literature. So we have this notion of type enrichment through extension methods on existing types. Now, you can also add generic extension methods. So we can, for example, create a method to combine all the elements on a particular list as if the combine all method belonged to the list type. And at the same time, this feature of extension methods in Scala can also be combined with contextual parameters with great success and a lot of expressiveness and power. So I can define extension, which takes a type argument A. So considering a type A and a list as a list of A, then I can define a method, let's call this combine all, but I'm going to say combine all values so that we don't really have a name collision with this other combine all method. And combine all values will take a contextual argument, so using combinator as a combinator A, and this will return an A, and I can write the same implementation. So list.reduce with combinator.combine. Now with this little piece of code, then I can say, val, let's call this the sum version 2. I can then say a list dot combine all values. Just like that. So I can recompile my code and the code will work just as fine. And if I do print line the sum v2, then we're still going to see the number 10 to the console. So we have it here. So notice how powerful our APIs can be. They seem as though they always belonged to the list class in this case, and also combining the power of contextual arguments that will make for a very expressive and powerful set of APIs and language. Now, contextual abstractions are an advanced set of features, and there are other forms of contextual abstractions that Scala supports, such as defining and inferring type classes, implicit conversions, or contextual function types, a bit outside the scope of this video, but I'm going to cover them in the advanced Scala course due shortly. So I hope you enjoyed this video, and waiting for you in the Rock the JVM website, in the courses, and on the Rock the JVM YouTube channel. I'm Daniel, signing off.